Friends, a very good evening and welcome to the 8th A P Mitra Memorial Lecture. I am Amitabh Sengupta and the General Secretary of the Indian Radioscience Society and the Chair of A P Mitra Memorial Lecture Committee of the NPL Former Scientists Forum, and I shall be the moderator for today's program. Before I begin, may I request all of you, except the speakers for the day, to kindly switch off your cameras and mute your microphones for a smooth conduct of the proceedings. A warm welcome to all of you to our annual A P Mitra Memorial Lecture event in the memory of Dr. Ashish Prasad Mitra, one of India's greatest radio scientists. Every year, we organize this event on this day in recognition of Dr. Mitra's significant contributions in this field. This year, the 8th A P Mitra Memorial Lecture is being organized jointly by the NPL Former Scientists Forum, the Indian Radioscience Society InRaSS, and CSIR-NPL. It will be delivered by Professor Dipankar Banerjee, Director, Aryabhatta Research Institute of Observational Sciences, ARIES, at Nainital, Uttarakhand, India. Professor Banerjee is a renowned astrophysicist with a specific interest in the sun and the solar atmosphere, and we are extremely thankful to him for accepting our invitation despite his very busy schedule. Now, to begin our program, I'm glad to inform you that we always have had unstinted support to our organization from the family of late Dr. A P Mitra. This time has been no exception. I now invite his daughter, Dr. Patralekha Mitra, commonly known as Mila Mitra, to pay our respects by garlanding Dr. Mitra's photographs and offering floral tributes. Mila and her spouse, Professor Krishna Achyuta Rao, are in the audience and will pay tributes. I invite all of you to join us in paying our respects to Dr. Mitra. Mila, please. Mila, please unmute yourself because otherwise you're... Okay.
Hello, everyone. I will now light the lamp. On behalf of our family, I thank you for holding this lecture in my father's name, and I welcome Dr. Dipankar Banerjee for giving this lecture. Thank you.
Thank you, Mila. May I now invite Mr. R.B. Saxena, who is the General Secretary of the NPL Former Scientists Forum, to say a few words about the A P Mitra Memorial Lectures and the NPL Former Scientists Forum. Mr. R.B. Saxena, please.
Thank you, Dr. Sengupta. Let me welcome all the guests. Dr. Dipankar Banerjee, Director, Aryabhatta Institute of Observational Sciences, ARIES, Nainital. Dr. Venugopalachandra, Director, CSIR-NPL. Dr. S. Ananthakrishnan, President, Indian Radio Science Society. Dr. Amitabh Sengupta, Chairman, AP Mitra Memorial Lecture Committee. Dr. J.C. Sharma, President, NPL-FSF. Shri N.K. Vadva, Secretary, FSF. Family members of late Dr. A P Mitra, NPL Former Scientists Forum colleagues, NPL fraternity, distinguished participants from Indian Radio Science Society and abroad, audience watching this event through YouTube broadcast, ladies and gentlemen. On behalf of NPL Former Scientists Forum, I, in the capacity of the Vice President of NPL-FSF and the convener of the A P Mitra Memorial Lecture Program, welcome you all to the 8th A P Mitra Memorial Lecture today, which is going to be delivered by Dr. Dipankar Banerjee on Aditya L1, India's Space Laboratory to study the variability of our dearest star, the Sun. Let me just say a few words about NPL-FSF. NPL-FSF was founded 19 years back by our senior distinguished colleagues who nurtured it with great care till date. The NPL Former Forum is a professional, social, non-profit organization with a pool of talent, expertise, and experience, and carries out several initiatives for the promotion of science among researchers and the young budding school college students by giving away several scholarships and awards to meritorious children of the NPL staff and the retired personnel. The forum also takes care of the welfare of the retired scientists of NPL and helps its members to overcome problems related to healthcare, family pension issues in cooperation with NPL administration, which shows great compassion. Forum also make important publications, for example, annual newsletter and directory of members, which have been extremely useful to the members, which work like a binder among the members. Forum also organizes lectures by experts in the field of science, new technology, healthcare, and personal safety of elderly persons. NPL Former Scientists Forum has instituted an annual lecture series in 2014 in the memory of one of its very distinguished former patrons, the late Dr. A P Mitra, FRS, ex-Director NPL and ex-DG-CSIR. This lecture series aims at providing a platform to honor the lifetime contributions of late Dr. A P Mitra to radio and atmospheric sciences in India and on an international level. These A P Mitra Memorial Lectures held at CSIR-NPL have been organized jointly by NPL Former Scientists Forum and National Physical Laboratory. And National Physical Laboratory. The holding of APM Annual Lecture Series is supposed to be primarily funded by an endowment created out of the contributions from the SY National Organizing Committee of RCGA 2005, the late Mrs. Sunanda Mitra, wife of late Dr. A.P. Mitra, Dr. Mitra's family, Dr. K.K. Mahajan, and former students and associates of Dr. Mitra. Earlier, 7 A.P. Mitra lectures have been delivered by eminent scientists and research in the field of radio and atmospheric sciences with the late Professor Govind Sarup, Dr. Krishna Swami Kasturirangan, Dr. Shivaji Raha, Professor S. Ananta Krishnanji, Dr. Achanta Bhattacharya, Archana Bhattacharya, Dr. Anil Bhardwaj, and late Dr. Patricia S. Johati. The 8th Epimetamor lecture has been organized jointly by NPL Former Scientists Forum, and India Radio Science Society as a webinar. We look forward to an enlightening lecture. Thank you, sir.
Thank you, Saxena ji. Friends, in our organization of the A.P. Mitra Memorial Lectures, we have always been fully supported by the CSIR-NPL, a place which has been the workplace of Dr. Mitra for close to 5 decades. Before the COVID pandemic, the APM lectures had traditionally been held at the NPL auditorium. This time too, the director NPL, Professor Achanta Venugopal, has kindly provided his full support. He has also kindly agreed to preside over this function. Professor Venugopal, Director CSIR NPL, unfortunately couldn't participate due to his prior engagement, but has sent us this recorded video, which I shall play now.
I welcome you all to this A.P. Mitra Memorial Lecture to honor one of the visionaries who led not just CSIR-NPL but also the CSIR family. He has put CSIR-NPL on the world map in the area of environmental sciences. We all know this. CSIR-NPL is well known for metrology, material science, and environmental sciences. So for material science, we have Dr. S.K. Joshi, another visionary, and of course our founding director, Dr. K.S. Krishnan, who is a pioneer in his own right in Indian science. So honoring these stalwarts is our basic responsibility and duty to remember them and pay tributes to them. So for that reason, like I really congratulate and commend the Former Scientists Forum of CSIR-NPL for being at the forefront of science popularization within the country, and then to remember these stalwarts and giving the younger generations a chance to listen to the leading experts in the field, as well as remembering our own forefathers. Thank you once again, FSF, and welcome you all to CSIR-NPL for this A P Mitra Memorial Lecture. Thank you.
Thank you, Dr. Venugopal. Now, friends, we are very grateful to the Indian Radioscience Society who are partnering in the organization of this event by providing support in some key technical and other aspects. The formation of the Indian Radioscience Society was primarily motivated by pioneering initiatives taken by Dr. Mitra to promote research in radioscience in India and in the developing world. It is my pleasure now to invite Professor S. Ananthakrishnan, the President of the Indian Radioscience Society, to say a few words about Dr. A P Mitra. Professor Ananthakrishnan, please.
Thank you. Thank you, Professor Gupta, for this introduction. On behalf of the Indian Radioscience Society, I feel privileged to talk about late Dr. Ashish Prasad Mitra, the doyen of radioscience in India, whom I knew very well during his lifetime. He and I belong to the same alma mater. He was, of course, 12 years or so senior to me in the college, in the radio physics and electronics of Calcutta University. Dr. Mitra initiated the regional facility for radio science of the International Radio Science Union, which has morphed into the Indian Radio Science Society of today. And I am representing that, as Dr. Sengupta mentioned. Dr. Mitra was the director of the National Physical Laboratory from 1982 to 1996, and the Director General of the Council of Scientific and Industrial Research, CSIR, from 1986 to 1991. He was well known all over the world for his work in radio and atmospheric physics. To give you a brief history of Dr. Mitra, Dr. Mitra was born on February 21, 1927 in Kolkata. A brilliant student all through his educational career, he had stood first in all his major examinations. After passing the Master of Science in Physics from Calcutta University, he joined Professor Shishir Kumar Mitra, who was again a student of Professor Acharya Jagadish Chandra Bose. And Shishir Mitra was a pioneer of radio science research and ionospheric research in the world since 1930. Younger Mitra's D.Phil degree from Calcutta University on this subject took place at a time that was considered the golden era of Indian ionospheric research, and it marked the first step of a brilliant scientific career. Dr. Mitra joined the National Physical Laboratory in 1954 as Secretary of Radio Research Committee. And soon afterwards, he set up the Radio Science Division at the National Physical Laboratory, marking the beginning of an association that was to last till the very end of his life. As a successor to his mentor, Professor Shishir Mitra, Dr. Mitra carried the ionospheric research program forward at the NPL in collaboration with several other Indian groups from all over India. Dr. Mitra's research topics involved the Earth's near space environment, first with the ground-based and later with space-based techniques. As Secretary, Indian Committee of the International Geophysical Year, he steered the Indian program for the International Geophysical Year, as well as the International Quiet Solar Year during 1957-58, which pushed Indian efforts into international limelight and ushered in a new era of ionospheric chemistry. His pioneering research in cosmic radio noise for studying the upper atmosphere led to a series of discoveries in the ionosphere and solar physics. The 60s saw him working in the high-level atmosphere, probing with rocket-borne payloads. The 70s saw his involvement in developing scientific capability in radar and troposcatter systems. Under his guidance, the SITE experiment with radio beacons led to an India-wide effort on the studies of upper atmosphere. The Indian Middle Atmospheric Program, IMAP, of the 80s saw extensive use of balloons and rockets going into the upper atmosphere to carry equipments and study the ionospheric levels. The 90s saw his initiative with a new world-class effort, mesospheric, stratospheric, tropospheric radar, the MSC radar, which is installed in Tirupati now, and the SROS satellite with the specialized capabilities to access substantial parts of the atmospheric environment from near the surface to around 1,000 kilometers for physical properties like electron and ion temperatures, as well as densities at different levels. During the last decade, during 2000 to 2007, Dr. Mitra concentrated on global environmental changes from human activities and their consequent impact on the biosphere, and his contributions to the chemistry of the atmosphere and measurements of greenhouse are very important. And it contributed to the global environmental chemistry, including the measurements of methane emission from paddy fields. They have been significant. As a leading figure in international programs like the Indian Ocean Experiment, INDOX, he played a crucial role in the field of global climate change research, which was alluded to by the previous speaker, Dr. Vedagopal. Dr. Mitra was the recipient of many coveted honors and awards. He was a fellow not only of all the 3 National Science Academies of India, but also of some of the most prestigious academies of the world, especially of the Royal Society of England, the Russian Academy of Science, and Third World Academy. And his awards spanned a very wide range and included the Bhatnagar Award in 1968, C.V. Raman Award in 1980, FICCI Award in 1992, Modi Award in 1991, and Meghnad Saha Award in 1992, and the prestigious Padma Bhushan of the Government of India in 1987. He was president of the International Union of Radio Science for a term, his professional standing notwithstanding his human qualities, such as love for cricket, for which India has an addiction, and Ravindra Sangeet, and his enjoyment in fraternizing with fellow colleagues was no less than evident during his lifetime. And whenever I walked into his lab in Delhi, he always opened up his arms and he welcomed me with great love and affection, and it was great to have a meeting with him at any time of the year. One of his last scientific acts was an authoritative account of the progress of ionospheric research in India, starting from the pioneering efforts of Professor Shishir Mitra and duly carried forward by the NPL under his own dynamic leadership as a chapter in a book entitled India in the World of Physics, Then and Now, by A.N. Mitra, edited by A.N. Mitra in 2007. He passed away on September 3, 2007, after a month's illness. Only a few months earlier, his 80th birthday had been celebrated at NPL, the institution with which his name had been inseparably associated with for the last half a century, from 1950. He was survived then by his wife, Sunandadi, and 2 daughters, Anusuya and Mila, who you have seen a little while ago, and their respective families. Mrs. Sunanda Mitra too passed away soon. Our humble homages to both of them, and may his name live for a long time in the Indian and the world radio science community. Thank you very much.
Thank you, Professor Anand Krishnan. Friends, now finally we are ready for the 8th A.P. Mitra Memorial Lecture entitled Aditya L1, India's Space Laboratory to Study the Variability of Our Nearest Star, the Sun. It will be delivered by an internationally renowned astrophysicist, Professor Dipankar Banerjee, and it's my pleasant duty to introduce the speaker for today. Professor Dipankar Banerjee is currently the director of the Aryabhatta Research Institute of Observational Sciences, ARIES, in Nainital. He is an astrophysicist with a bachelor's degree in physics from St. Xavier's College in Kolkata and master's degree in theoretical physics from the University of Kolkata. He has obtained his PhD from Indian Institute of Astrophysics and completed 2 postdoctoral tenures in reputed institutions in Europe. He is also a senior professor at the Indian Institute of Astrophysics in Bangalore. Dr. Banerjee's area of interest is the sun and the solar atmosphere. His work involves theoretical and numerical modeling using data from ground and space-based instruments. His work has enriched our understanding of the sun and its impact on the space weather. He is the co-chair of Science Working Group of the Aditya mission. Aditya is the first dedicated Indian mission to study the sun, expected to be launched by Indian Space Research Organization around 2023, that is next year. Dr. Banerjee is also involved with the NASA's Punch mission. He is an honorary fellow of the Indian Academy of Sciences and the National Science Academy and is currently the president of the Astronomical Society of India. Dr. Banerjee has more than 140 peer-reviewed publications with around 3,300 citations in international journals. He is currently supervising 6 PhD students, while 13 of his students have already completed their PhDs. Now, this is the interesting part. Apart from his scientific career, Dr. Banerjee has interest in various other activities. He is trained in Hindustani vocal and is a part of a Bengali theatre group, Smarani, and regularly performs in plays, participating in national and international theatre festivals. Dr. Banerjee's love for science and zest for life are infectious. With this brief introduction, I have great pleasure in inviting Professor Dipankar Banerjee to deliver the 8th A P Mitra Memorial Lecture. May I request all the rest of you who are logged into the WebEx meeting to kindly switch off your cameras and microphones. Professor Banerjee, the floor is all yours. We are looking forward to your talk on this fascinating subject. Thank you.
Thank you very much, Professor Sengupta. I hope my voice is very clear. I just need to confirm that.
Yes.
Slides are clearly visible.
Correct. Thank you. Yes.
Thank you very much. It's a privilege and honor for me to get this forum to give this lecture. I'm really a bit nervous because the predecessors who have given this lecture are really, really renowned people, nationally and internationally. And I'm much smaller in that context, but I hope I can live up to that standard. And also, it's a really honor for me, originally from Calcutta. Last week only I was in radio physics department, and I was attending the lecture of former ISRO chairman, and in the Meghnad Saha auditorium, and Shishir Mitra's legacy was all around us. And to get this opportunity of the same Shishir Mitra and Professor A P Mitra and their legacy, it's our pleasant duty to probably make things more popular to the general public and audience. So again, thank you very much for giving me this honor. I consider this to be an honor for me to get this opportunity. So let me get into my subject area, which is our nearest star, the sun. And I will be talking about this mission, which is really one of our milestone mission from Indian Space Organization. So before I go there, I will probably talk about why do we need to study the sun? And of course, now in modern day, we know that our existence and our atmosphere is very much within the heliosphere. So we need to study all these as a coupled system. So I will get to that side. Very briefly, this is the place where I am right now. This is the Manora Peak in Nainital, and I'm sitting right here in this particular small little window here, you see, and the beautiful, the ground stations you see here. This used to be called the UP State Observatory. Now it is called ARIES, but we do have a new campus in Devasthal. So the audience, you're all most welcome to visit at some time. I'll be happy to host you here in our campus or in Devasthal campus. Sun is our nearest star, but it's a normal star. It's middle-aged. It's going through its stellar evolution, and still it's going to be there for a pretty long period. You don't have to worry about it. But it is a special star because it is the only star in which we can really resolve the spatial scales on which the fundamental processes takes place. Most of the astrophysical objects in the sky, we see them as a point object. And we do get the radiation, and we could get the particles also sometimes from there, but they are far away from us. So we really cannot really see that much of details on the surface of the sun, of that particular object or its atmosphere. Whereas sun, being closer to us, we are able to resolve the structures. It is also, of course, a special star because it provides almost all the energy to Earth. So our existence is just because of the presence of the sun at an appropriate distance away. So I think it is a very, very important subject to study very closely. From a physics point of view, it is also a very special star because it provides us with a unique laboratory in which to learn various branches of physics. I mean, if there are physics students in the audience, and if you have questions on nuclear physics or in atomic physics or molecular physics, you name any branch of physics, you will find an application in the sun. And also the point is that the universe, we have 99.9% of the universe is in the plasma state. This is the fourth state of matter, and certain plasma physics experiments, it is very difficult to conduct in the laboratory in our environment. So to achieve certain very high temperature or very high density or pressure, it is impossible to achieve that within our laboratory environment. Whereas in the sun, we find such conditions, such physical conditions, which allows us to verify our theoretical understanding of that plasma physics. So as you know, physics remains as a hypothesis unless it is experimentally verified. So in that context, sun really provides us a unique laboratory as well. Then we think that sun, like all stars, is probably in a very static up in the sky, but in reality, they are not. They're very dynamic, they're always active, and they're always changing as well. So more we learn about our nearest star, the sun, we can actually extend that knowledge to understand the other stars. And it is an ideal laboratory for, as I already indicated, for plasma physics, for atomic physics, particle physics, nuclear physics, spectroscopy, you name it. Here, I'm showing you a movie from one of the space, laboratory called one of the NASA, mission. And there you see there are regions in the sun where you have certain regions which are comparatively brighter than the other regions. And here you see after a certain time, there is some instability and the material which is confined in that region get exploded. Some material is thrown into interplanetary space and some material goes back to the sun. When it interacts with the, in the surface of the or lower atmosphere of the sun, there is again, a brightening. That means there is a local temperature changes and so on. So these kind of, strong emitting regions are called active regions. And they're called active because they're very dynamic and there are some kind of variability. And this variability could be of the order of minutes, could be order of hours, could be order of, months also. In comparison to these active regions, in the surrounding regions, traditionally, they used to be called quiet regions. But today, because of the modern, observational capabilities, now we know that in the sun, nothing is really quiet. It's just the variability or the structures of these different regions are different. The places where these kind of very, very strong, emissions are coming, now we know that these are the regions where there is a presence of strong magnetic field. So this is the main driver of all the variability what we see in the sun. And because of this magnetic field presence and its variability, actually the sun is one of the most interesting subject to study. Here, these bright regions, what you see is that there are structures. These are kind of, loop-like structures. They are called magnetic loops, and they're confined because of the presence of the magnetic field. And if these magnetic field structures are, for some reason, they get disturbed or unstable, then the material which is confined, they're thrown into interplanetary space. So I will now go back to this, story of these magnetic regions. Those magnetic regions are called sunspots, as first recorded more than 400 years back by Galileo Galilei. And he used just the very newly invented telescope at that point of time, and then he started looking at the sun. And the animation which is shown here is essentially, it's just a hand-drawn, diagrams of Galileo Galilei. If we just put consecutive days, he's drawing and make a animated movie, what we clearly see is that these dark regions on his drawing, these are sunspots. Of course, he didn't know about the presence of the magnetic field at that point of time, but he found out that these are kind of dark spots on the surface of the sun. And the other thing which he could immediately notice, that the subsequent day, you see these dark spots moving towards the right. So that gave him a clear indication that the sun is also rotating around its own axis. So again, Galileo Galilei and Christoph Schreiner noticed already that the sunspots move across the solar disk in accordance with the rotation of a round body. And then they mentioned that this is a rotating sphere. Of course, again, at that point of time, Galileo didn't know that sun is not rotating as a rigid body, but it rotates differentially. Now we know that the solar equator rotates faster than the pole. And this is what is called differential rotation of the sun. That again makes life very, very interesting and complicated. You can just imagine that I'm just standing on somewhere and my tummy is rotated much faster than the head. What kind of stresses would be applied within my body? And you can think same thing is happening inside the sun as well. So I won't go much deeper into the interior of the sun, but today I'm primarily focusing on the surface or the atmosphere of the sun and the changes what happens in the atmosphere of the sun, which impacts our, Earth and planetary atmospheres as well. So here, if I look at the sun from a white light image, some days, there are hardly any such dark spots. Sun becomes boring. Some days there are these kind of, spots. And if I now look at little more closely, these are always comes in pairs. There are certain features you see, they are typically happening more closer to the equatorial belt. They are not seen to the very, very high latitudes in the case of the sun as well. If I now sort of zoomed up this particular sunspot, I will see much more details of these sunspot pairs, and often you will find it's just not the pair of sunspots. There could be, many, many different spots, and all together they are called active regions. And just for comparison, you can imagine if it is the size of the Earth, how big are these concentrated magnetic field? So that's my laboratory or a magnetic confined plasma. You have heard about tokamaks. It's very, very difficult to have these confined plasma experiments in the laboratory. To build a tokamak of few tens of meter, it costs several hundreds of crores. And here I have a laboratory in space, which is several megakilometer size of a tokamak. So that's the reason several of astrophysical or plasma physics questions are now being verified with astrophysical experimental domain. How does the sunspots come from? the sunspots are magnetic structures, as I already mentioned. They emerge from beneath the surface. And this animation again shows you that these white lines are basically bundles of magnetic field lines. If you recall your experiments in the school, that you have a bar magnet and then you have sprinkled iron fillings, you know that the iron fillings takes a particular shape and a particular path they follow, that they are called the magnetic field lines. And these magnetic field lines, if you have millions of magnetic field lines together, they are called magnetic flux tubes. So what we see here in this kind of animation is presence of these magnetic flux tubes, and they are always comes in pair. As I said, one will be north polarity and the other will be the south polarity. But what is happening here is that these tubes, they are actually lighter than the surrounding. You can think about a rubber tube, submerged in a bucket of water. And when the rubber tube is light, you will see that they will float. They will come up on the on the surface. So exactly that kind of thing happens here in the sun. These flux tubes are generated inside the sun, and they come up because of buoyancy. They're called magnetic buoyancy. And here you saw that because of these lines being tangled, and they break apart, and then that really creates this explosion. They are also called the solar storms. So we have to worry about these solar storms when it comes to our Earth and all that. So this is a kind of variability which I was talking about, which is in number of hours or days. Now, if I look at the last 400 years of history of sunspots, what is plotted here is sunspot number on y-axis, and this is the number of years for last 400 years. I see that there are alternate peaks in the solar activity. Some period it's called maxima when the sunspot numbers are high, and there are times when the sunspot are hardly there are sunspots. They are called minima. Typically, their periodicity is about 11 years. But what is to be noted here is that the strength of the cycles are very much variable. Even if I look at the last 100 years, you could see that around 1957 this cycle was much, much stronger than these other cycles. And this is called the solar cycle. Incidentally, Samuel Swabe, he observed the sunspots only for this period. And you can see these, the scientists had so much of, intuition and vision that just by observing these two, kind of periodicity, he sort of discovered that there is a, alternating, solar behavior, and he named it as a solar cycle. So now, when we look back into the history of this, entire together, we also observe a very, very peculiar behavior in 1650 to 1700. There were hardly any sunspots recorded. And what was the impact of that? Europe was extremely cold because science was developed there and the things were recorded there. The river Volga was frozen for 30 years. So that means if there are no sunspots, somehow the solar radiation gets impacted and we get global cooling effect. So obviously, we are all, worried about global warming. So you can imagine if sun becomes more active, then probably it will add on to our global warming, which is primarily, we are responsible for that, for industrialization and so on. So it is important to really, really follow the total solar radiance, which is considered to be constant, but now we know that is strictly not true. There is a 0.01% variation, and if it varies more than that or less than that, then what could be the impact on our climate? So that's again a different kind of variability, but the physics of that is very, very different than when we are talking about the variability of minutes and hours. So in a way, just if one wants to study the different kinds of variability, one can apply different kinds of data sources, one can apply different kind of physics and come up with all these, because the long-term variability has an impact on our climate, long-term climate, whereas the short-term variability has more impact on our space weather variation. I mean, on a day-to-day basis, the kind of, communications. In fact, this forum is, primarily for the radio sciences and the ionospheric research, and Professor Mitra's work has been fantastic in this ionospheric domain. In fact, when I started my PhD, I remember that these communities were not talking to each other so frequently. ionospheric disturbances are now, we know very clearly, is because of the presence of all these solar storms and so on. So unless we are able to, understand the source of these storms, unless we are able to predict the solar storms, we'll not be able to study the impact. When does this ionospheric disturbances are likely to happen? When our GPS is going to be, problematic in our communications and so on. So this system is really, becoming more coupled thing. And I'm actually that way, quite honored that Professor Anand Krishnan, when he approached me some 6 months back, I understand I'm not from a radio science background, but the way the modern science is looking at how it is important to study this coupling is really very important. So in just this context, I just like to highlight that in our within the country, we have a fantastic data source in Kodaikanal. If you because we have been looking at the sun for last more than 100 years, and we have, if you just go back to the archive now, we have digitized all this data, and all the data is available to the whole global community. If you just go back to 1st January 1958, we have observations in multiple wavelength. Actually, multiple wavelength probes different layers of the atmosphere. I will come to that very soon. And that resource is available. And it's actually from this side, there were also ionospheric, active research, which is not continued, unfortunately, now. But I think the idea in 50s and 60s was to have the ionospheric research and the solar research on the same venue. And unfortunately, it has not been continued, but I think it is a very important area, and I thought I will highlight that as well. So my next focus will be that why do we need to really highlight the multi-wavelength aspect of astronomy in general? And for sun, it is no different. When I just look at sun through an optical telescope in this, you see there's 1 or 2 sunspots and so on, but not too much of details. But when I go to higher wavelengths, of course, this is just an infrared. I should probably have included another radio map of the sun. There are fantastic work happening from GMRT as well. And we have our own Boribidanur, array as well. From there, there are coronal observations and all that. But I have not included those elements too much here in this particular presentation, but they are very, very important to cover all the way from the long wavelength to the shorter wavelength. What happens is typically the shorter wavelength emission comes from the extended part of the atmosphere of the sun, which is called the corona. And here you see that when we go to space, then only we can really see these shorter wavelengths. And once we started going to space, astronomy has really gone multifolded. So now, even for general, astronomy, how important it is to combine the millimeter wavelength, the radio wavelengths, and then, people have just, James Webb is showing a completely different picture because they're getting the kind of infrared emissions. So my, again, emphasis is that today we are getting into an area or a domain where we do have to think about all, aspects of the wavelength, domains. And we are lucky that from India, we have got this opportunity of a space mission, and simultaneously we are looking at a ground facility as well. So if I just look at the photosphere with one particular wavelength, this pair of sunspots looks like something like this. And then we go to slightly higher atmosphere and look for the calcium line. I showed earlier also the calcium line image from Kodaikanal that was full disk. These are from space observations. And if I do the same thing from H alpha, I see much more details when finer structures. It's the same region, but when we see at different wavelengths, we are able to actually probe different layers of the atmosphere, and we are able to study the coupling, how the things happen in the surface and their motions and their changes in the magnetic field, how it affects in different atmospheric layers that we are able to study because of the presence of this, multi-wavelength observation. So this is a typical temperature profile of the atmosphere of the sun. You see here, the interesting aspect of the atmosphere of the sun is the temperature profile, is that when we go from the surface to, say, about 500 kilometers, the temperature drops. And that is what you expect. I mean, if I go from Delhi to Nainital, it is cooler. And if I go further higher, it is still cooler because all the heat is actually on the surface only. But in the case of the sun, it is very, very different. Beyond 500 kilometers, if I go up, temperature starts rising up, tens of thousands of Kelvin of temperature up to 2000 kilometers. And then suddenly within 100-kilometer radius, the temperature jumps to 1 million K or higher even. So this is a very unusual, no normal thermodynamic processes can explain. So obviously there are non-thermodynamic processes, non-thermal processes, which we now understand explains this high temperature of the corona. We have quite a bit of understanding, but still there are a lot of loopholes in our understanding. We still cannot really get the complete budget of the energy which is required to maintain a high temperature of the corona. So again, highlighting, these are the active regions which I was referring to all through. These is a photospheric height observations. You see presence of strong magnetic field. If I go to 2000 kilometer height, I see these magnetic field regions are connected by these kind of loop structures, and lots of plasma material is confined within that. And these temperatures are the millions of Kelvin temperature because these corresponds to highly ionized emission of iron lines. And these images are taken through filters which are sensitive to certain ionization, of these elements as well. This particular picture is about a chromospheric representation. As you see here, these are also structures, but they are not so much extended and big ones. So that's how you can build this, picture that we have a pillar which is anchored in the ground, which is the foot points of these pillars are these magnetic field, and they are sort of solid structures. Sometimes they're curved structures connecting one polarity to the other polarity, and they are very dynamic. And if they are, shaken, if they're twisted, then material which will be confined within that will be rupturing and then coming out. That is again a sort of picture of the active region. I will show you. I will jump into even a quiet region. As I mentioned earlier, it was understood that these things are quiet, but now you will see with a very high resolution observations of the ground. These are observations taken from Goody Solar Telescope in US in Big Bear Solar Observatory, and I'm combining with this Goody Solar observation with the space-based observation. I see these kind of locations where there were presence of these strong magnetic field. These kind of jets are produced, and how these jets are produced? These jets are produced because of the magnetic cancellations between opposite polarities. These blue ones are the positive polarity, and the red ones are the opposite polarities. And you see when they come closer to each other, they cancel, and these jets are forming. So these jets are coming exactly at the locations where these magnetic cancellations are happening. So these are called, spicules. And then if we can follow these jets all the way up in the corona from space observations, I will see that wherever these jets are present, there are presence of these strong brightening. So the brightening means, lots of heating in the localized region. And that is now been able to explain that these kind of, things are coming all the way from the photosphere and then going up in the high up in the corona. So that's the behavior in the so-called quiet region as well. So I just wanted to point out that in the sun is really, really very dynamic. It's just not that, wherever there is sunspots or these active regions, there are dynamic things happening. Everywhere there are certain dynamics happening. The time scales of those variations, spatial scales of those variations are different. In the past, we were able to see only the big guys, and the small fellows were not being seen, and they were insignificant because of the lack of our observations. But now what has happened is, because of the presence of very big telescopes in the ground and in the space, we are able to really dig much deeper into those regions, so-called quiet regions, and we are discovering many more dynamic phenomena. So here, these are the storms. When the magnetic forces above sunspots become tangled and break apart, violent storms can burst into the sun. This is the main source of our strongest space weather events, either coronal mass ejections or flares. And these white specks which you saw at the end of the movie is basically because of these high energetic particles, and the protons which is coming out of these blast is hitting the satellite. The detector is taking remotely the pictures of these events, and when the particles hit the detector, you get this kind of snowflake kind of behavior. So obviously, instead of the detector, if I am sitting there, I don't be very happy to be hit by this, bombarded by this amount of particles. So flares are quick, intense, but smaller explosions than coronal mass ejection. So here certain movies of these flares you are seeing. And again, I'm showing the flare movies in multiple wavelengths. See, these are more chromospheric feature, about 1,000 kilometer from the surface of the sun. And if so this is again seeing this zoomed up portion when such a flare happens, bright flashes, sometimes followed by a burst of high energy particles, and that can travel half the speed of light. Large flares can occur several times a year when the sun is near its peak activity. As I said, the number of sunspots being more means, more magnetic activity. Here you are seeing a coronal picture, and here this is the flare, and then this material is thrown into the interplanetary space, and we need to really understand why there is a flare at certain point of time, and then if there is a flare, how much energy is going to be ejected, and when it can reach our satellite or our near Earth environment as well. So all the communication systems and ionospheric effects are primarily because of these solar storms. CMEs are larger solar storms, and that can blast out clouds of billions of tons of particles. You see example here at over 2 million kilometers per hour. Smaller ones can occur almost any day, but the bigger ones essentially is related with bigger active regions and so on. And it takes typically 1 to 3 days, but it is to be also noted that we are in the 3D-dimensional space, and sun is also rotating around its own axis. It's not that always all these storms are really directed towards us. It can go to some other directions, and it may not hit us. Having said that, there are other satellites and so on and so forth in different space, in different domain. Out of ecliptic satellites are also there now, so they get affected. And sometimes these CMEs, which they are coming out of the sun, they get reflected because of the interplanetary magnetic field structures and all that as well. So we need to understand the entire environment much better. So how do these CMEs are tracked? Apart from those imagers, we have another instrument called the coronagraphs. Basically, coronagraphs are creating a total solar eclipse kind of scenario. You block the solar disk, then only you can see the outer portion, outer radial emissions. And there you could follow these structures into much greater detail. So by combination of imagers and coronagraphs, and even I will show you some other examples of heliospheric imager, we are able to track these CMEs as it comes out of the sun all the way to Earth. I would also point out here you see movies of these ejecta taken from identical satellites from 2 vantage points. So the advantage of 2 vantage points is that you are able to do a stereoscope. You see, unless you get a stereoscopic picture, you actually cannot really characterize the properties or the speeds of these objects which is coming towards you. If something comes out of sun and directly comes towards you, you are basically seeing that object on the plane of the sky. So from those measurements, you cannot exactly calculate the velocities of these objects and so on. Whereas if this object is viewed from the sides, from the 2 sides, and then you are able to take a stereoscopic reconstruction, then you will get a much better estimate about the speed of this ejecta as it travels from sun to Earth. So these are the real changes which is happening, and we have multiple satellites which is being used to track these. So the sun is also the source of radiation and storms that we call today space weather. This is again a movie taken from the stereo spacecraft, as you can see. And from these movies, you can imagine that it's not a very pleasant environment to walk around and so on. So the space weather is really a big thing now, and their industry very much worried about it, because people are thinking of going to space in person. it's just not one of moon mission. We are talking about making colonies in other planets. And of course, our telecommunications, other things are also very much dependent on the space weather. So what is important is to track these ejecta as it comes from the sun all the way to Earth. So you cannot do it with a single instrument. You have to have a imager which is really able to capture the features in the close to the sun. Then you have coronagraphs. So here these are two coronagraphs. These are all the instruments are in stereo spacecraft. So you can imagine all the spacecrafts are getting equipped with multiple payloads with multiple wavelengths and so on as well. So here I'm showing only a combination of white light stuff and UV stuff. Here it is a EUV image, and then you have two coronagraph, and then this again, this is a white light. You have heliospheric imager, which is able to track all these guys all the way it comes to Earth. And it can also, essentially study the impact of, other planets and planetary systems as well. We live in the atmosphere of the sun, basking in its light and warmth, protected by our own magnetic shield. If Earth would not have its own magnetic field, our existence would not have been there. And here it shows that how a normal magnetic field is getting completely, modified because of the presence of this radiation and the particles which is coming. So far, I did not talk about the continuous, expansion of the outer atmosphere of the sun, which comes from the solar wind. Basically, sun also loses our amount of mass, very, very tiny mass, but it's sufficient to, make this kind of changes in the Earth's magnetospheric environment. This is called the solar wind. And solar wind also is quite dependent on the magnetic activity on the sun. It is not that the sun is symmetrically, expanding or losing out some mass in all directions very systematically. There are lots of, variations in terms of the latitude, in terms of the different phase of the solar cycle, and so on. So we need to understand the magnetic field again on the global structure on the sun as well. So this is a very, very important element as well. So space weather refers to the changes in the space environment near Earth. So sun releases this amount of energy in the form of light, in the form of particles, electrons and protons, and also magnetic field. Basically, these magnetic regions, when this ejecta comes, that ejecta actually carrying substantial amount of the magnetic field as well. So that's why we call them magnetic cloud. And these magnetic cloud all the way travels and interacts with Earth's magnetosphere, and it produces all kinds of effects. And you will see that if you are within this magnetosphere, then probably you are still protected. But if you go outside this magnetosphere, you are exposed to these, all these space weather effects. And how this space weather is, being controlled, as I mentioned, there is activity cycle 27 days, just solar rotation. There is also, 100 days typical time scales. People think about the active region development, like, how long that active region will last and so on. Of course, there is a 11-year solar cycle I mentioned, and actually there is a polarity reversal happens in the sun every 11 years. So if you include the magnetic cycle into consideration, then it becomes 22 years. There is also indication that there are much longer periodicity. It is not very, very well established yet, but there are substantial evidence that probably there are longer periodicities also in the solar magnetic activity. So all these will have effects on our climate and our day-to-day life as well. So impacts of space weather, as I said, there are cosmic rays and the solar wind, which I referred, and then you have solar flares. These satellites, they are every other day they are getting bombarded. In fact, not many are aware. There are lots of satellites which gets completely destroyed. There is an atmospheric drag effect. In fact, very recently there were SpaceX satellites which were launched, and a majority number of the satellites, 37, were lost just because they did not calculate the effect of the atmospheric drag because of a solar storm. There was a solar storm, and that because of the atmospheric drag, the satellite paths were all deflected, and they lost the track, and they lost the satellites eventually. And of course, if you are going in a space flight, there are a lot of impact of these, and people need to observe that. Of course, if there are stronger, storms, they will penetrate certain portions of the our magnetic shield, particularly with the high latitude. Those people who are in thankfully, we are equatorial region in India is not so, much better protected in terms of the magnetic shield. But if you are in a high latitude, like the Scandinavian countries or Alaska and so on, it does get affected. Canada had a lot of backouts in the electric grid disruptions. You can have problems with the navigation system disruptions and telecommunications and so on. So space weather is actually a real thing now. It is just not in a theoretical or on a scientific domain. It has a lot of its applications, and industry is worried about it, and we do have a role to play there as well. There is another point I thought, just one slide I will share with all of you is this multi-wavelength astronomy, how we are progressing in India. These are operational facilities. As you can see again, we are very proud to have really, really fantastic radio facilities within the country. We have certain infrared facilities. I didn't talk about our 3.6 meter telescope, which is there in our premises, the largest telescope in this part. AstroSat working fantastically for last 6 years, and of course we have shorter wavelengths, high altitude, fantastic new facilities in terms of the maze and so on. But if you look at the right side of the plot, thanks to again our space organization, we are thinking really, really big. We have n number of satellite missions which are on the card. And we are also partying to several mega projects internationally. We are partnered to TMT, we are partnered to SKA. I mean, this community, all of you are very much familiar with that. Of course, we are building LIGO India as well. So the point is really astronomy in a multi-wavelength facet in India is in a really, really golden era now. And taking the legacy of our predecessors and Professor Mitra and so on, radio have already established a internationally very, very sound position. I think in other wavelengths we need to catch up, particularly in the shorter wavelengths, and that's why the ISRO's role is very, very important here. That's the mission, Aditya L1. I will be talking about next probably 10 minutes or so. It's going to a long distance away from the sun. We'll be traveling about 1.5 million kilometers. Will take a little more than 3 months. It's called a Lagrangian 1 point. So, Earth center orbit, there is this transfer, then there is a cruise phase, and then we will be doing a big halo orbit around the Lagrangian 1 point. The idea is that we will have multiple payloads, combination of different wavelengths, combination of remote sensing and in situ instruments. We are going to a Lagrangian 1 point, so we have a huge opportunity to look at the sun continuously without any eclipses. So obviously it will be a very good vantage point to remotely look at the sun in multiple wavelength. We have a visible emission line coronagraph in the visible wavelength. We have also infrared channel within that. I will talk about it. We have a near UV full disk imager. We have 2 X-ray spectrometer, and we have 2 particle detectors and a magnetometer. It's a suite of instruments which are there on board. It is really, really a fantastic opportunity for the entire Indian community and the global community to participate in this, in this mega project. This is the complete list of the payload. As I indicated, coronagraph will be looking at primarily the corona. We'll look at the origin of this coronal mass ejections. Simultaneously, we have 4 cameras, 3 visible and 1 infrared. Through the infrared channel, we have a possibility of spectropolarimetry for the first time from space that will allow us to get an estimate about the magnetic field in the corona, which is still an elusive subject in terms of the solar physics. This is led by Indian Institute of Astrophysics. Then we have a near UV instrument fully resolving the photosphere and the chromosphere. This imager will allow us to look at the lower atmospheric layers. Because the coronagraph, we will look at the corona, and we'll be also looking at the total solar output or irradiance at these wavelengths. this particular continuous monitoring of near UV wavelength irradiance has not been done from space. So this is going to be the first time from space as well. We have two particle detectors aspects. One is built in PRL, one is in space physics laboratory in VSSC, into two different energy ranges. Solar X-ray spectrometers. These two spectrometers are going to look at, one is going to look at the small scale flares, and the other Helios one, which is built in PRL in conjunction with the Udaipur Solar Observatory in Udaipur, is going to look at the high energy X-ray counterparts as well. So we'll be able to capture all different classes of flares. And then of course we have the magnetometer in Lagrangian 1 point that will be allowing us to get an estimate about the magnetic field from these magnetic cloud. This is a very, very important element, because once we know the magnetic clouds, the magnetic properties, then we will be able to really predict the impact of that magnetic cloud as it hits Earth's magnetosphere. These are the different payloads in different locations. This is the stout view. At the top deck, we have this huge coronagraph of 170 kg. It's a luxury to have such a huge payload in space. I am aware, that in European Space Agency or NASA, nobody will allow you to fly a payload of such weight. But we are privileged here, and we are first time we are going to space with such kind of sophisticated instruments. So ISRO has been very, very accommodative, and we are going with a very traditional coronagraph, in space. And the suit is the near UV imager, which is there sitting next to the this coronagraph. This is the field of view of our coronagraph. We will be in one channel. We will be looking at the close to the sun up to 3 solar radii, 1.05 to 3 solar radii with the imaging in white light. But additionally, for the first time in space, we have spectroscopy, and that too with a multi-slit. Multi-slit spectroscopy allows us to, do things much faster. As many slits you have, that will actually, in this particular case, we have 4 slits. That will be 4 times at least faster from a traditional single slit experiment. So traditional astronomical observations are done primarily from a single slit experiments. And so far in solar case also, all space spectroscopy experiments have been done with a single slit. We are doing for the first time as a multiple slit as well. So these are uniqueness. Here again, I'm showing examples of the solar, coronal images taken from different solar eclipses with 2 different filters. One is called the traditional red filter, and the other one is called the green filter. And if I superpose these 2 images, it doesn't always overlap. So that means, corona is very, very multi-thermal. And if I look at 2006 and 2008, I see the corona has drastically changed. It has many more structures, and the temperature structures are also very different. Here we had hardly any green emission. Here we have more green emission. Here again, 2009 and 2010, as the solar activity increases and so on, you see a very, very different type of coronal structure. So it is important to study the corona continuously. These are 4 snapshots which are available only because of the total solar eclipse observations, which happens for a few seconds or few minutes, only. So what it boils down is this global field structure of the magnetic, sun is also very important. I showed you the evidence of active regions where there are sunspots which are about, say, tens of thousands of kilometers size in the photospheric height. I've also shown you the small little jets which are coming from the quiet sun, and those quiet sun jets are actually coming from 100 kilometer size magnetic field. And this is a global field structure. The 3D view of the sun, how it is the magnetic field, that essentially dictates how the solar wind will be, and how when the ejector comes out, how it will travel with the interplanetary field, because it will interact with the global field also. So its trajectory is completely dictated by the magnetic structure of the corona on large scales. So how this large scale magnetic field varies and so on and so forth. There are quite a bit of theoretical work which is happening already in India. My colleague Dibyendu Nandi from ISER Kolkata does this kind of modeling. He did this work actually just before one total solar eclipse, and he predicted how the corona should look like and how the magnetic field structure should be in the global field. And the next day when the total eclipse images were obtained, it matched up pretty well. So we are there. There are differences, and that allows us to make further improvement in our models. So the point is that there are good amount of work which is happening within the country. This is again another publication from Dibyendu, and then you see if you superpose the white light images and his magnetic field modeling, the prediction seems to be pretty good. Where these open structures, where these structures are closed, that basically controls the, as I indicated, the movements of these ejecta as it comes out from the sun, because it has to come out and interact with magnetic field lines and then escape from these areas as well. This is the near UV payload, which will cover, these regions. There are other wavelengths. This is again the temperature, profile of the sun. And then the SUIT instrument will primarily look at these temperature heights in the corona. It will have many different filters, which will probe, photosphere all the way to, to chromospheric heights. It also has 3 wide passband filters. These are the band passes. These are narrowband filters, and these are wide passband filters, which is important for atmospheric studies. I have no time to actually give you full details of this, but this particular payload has quite a few elements which allows us to see the ionosphere and the stratospheric influences of these UV radiation. Because we know now there are indications that the spectral irradiance in these wavelengths can vary with the solar cycle up to 20%. The total radiance, if we integrate the entire thing, it's not much. But at these wavelengths, the variations with the solar cycle is substantial, and that has not been monitored at all because there is no such space-based instrument available today. So this is the uniqueness. We have 2 X-ray spectrometers. One is going to look at 1 to 30 keV. Another one is going to look at 10 to 150 keV with a bit of overlap. This is the energy spectrum, and then here you see the Solex, and here it is the Helios, which will look at all the explosive energy release, particle acceleration, how the flares are triggered, what are the different cutoff energies, and soft X-ray, hard X-rays, the association of the flares with the CMEs and all that. So these 2 X-ray spectrometers will allow us to study the flares. These are the 2 particle detectors. One is going to look at composition of electrons and ion fluxes in the solar wind within this energy range, and then the aspects which is built in PRL will look at the anisotropy in the solar wind particle distributions, and with these kind of energy ranges, the different charge ratios and so on. I'm sorry, I'm not able to go into the very much details of these because they are slightly technical in sense. But point is that there are different regimes in the solar wind. There are regimes, again, this is what is shown here is the energy spectrum here. We have the slow solar wind, then we have the fast solar wind, the 3 keV range, which has a very specific detectors. Then we will look at the supra-thermal particles, 3 keV to a few hundreds keV. And then solar energetic particles, or ACVs, a few tens to MEVs. These are typically related with the big flares and so on. So that will allow us to look at the generation process, how these particles are generated from these big explosions, characterizing the properties of these particles, and then the distribution of the particles in terms of the 3D space, their anisotropy, and so on. So these particle detectors will allow us to do it. And finally, we do have a magnetometer. As I indicated, when there is this magnetic cloud, they are called the interplanetary CMEs, which will allow us to measure this magnetic field as well. So after all these, we need, community, support services and all that. I'm just using this opportunity to highlight that we have at ARIES, ISRO has given us a role to conduct many trainings many workshops, host a lot of youngsters particularly from the university sector, the people who are not dedicated yet in the solar physics. So we have built this service center at ARIES Nainital, and we have periodic workshops and so on. We had a couple of workshops, and the next one will be in IIT PHU in February. So the future lies, of course, with the youngsters. This is the group photograph from the Aditya Solar workshop, which people attended. This is my earlier research students gang. This is my recent student collection. I'm really hopeful that the opportunities what we are getting from India in terms of multi-wavelength observations from space and the ground is enormous. And these youngsters will take us to the next level. Thank you for your attention.
Thank you very much, Professor Banerjee. That was a fascinating lecture, and it was a really beautiful visual and pictorial description of the fascinating and somewhat, may I say, overwhelming description of the processes happening in the sun. You described in great detail, particularly with the help of beautiful visuals, those videos embedded in your slides, which made the processes so clear. Well, since the audience here is, and before I get to the questions, may I just say that all this is extremely topical, as you just rightly mentioned, that some of these extreme space weather effects could be really debilitating to the human civilization. It may wipe out the entire wireless networks that we have and cause devastations. So it's really important for us to understand all these processes. So coming to the questions, may I just say that we are afraid some of the questions that we pose will be somewhat naive, because it's a very heterogeneous audience, not specialists in solar physics or astronomy or astrophysics. So we've had some questions on the chat box, and I'll add some questions on my own behalf, and I'll request some of our colleagues, some of our friends who are in the WebEx meeting also to ask questions. The first question that we had was, right in the beginning, you said the sun is a very weird object. It rotates, but differentially. The belly rotates faster than the head and so on. Why? Is there a simple explanation for that?
Yeah. So one thing one should also remember, that sun is not a solid body in any case. So it's a plasma ball. So there is no reason that it has to rotate rigidly. If you take a jelly and try to rotate it and so on, you see always it gets deformed. But to be honest, it is not fully understood that why such a differential rotation like the equator takes about 27 days to make one full rotation and 33 days at the poles. That makes a sort of this differential things with the latitude very specific. But the point is, since it is not a rigid body in any case, it's a plasma blob, it is not necessary that it has to rotate solid as well. Incidentally, majority of the stars, again, I have not talked much about the internal structure of sun. So in the interior of a star, there are different layers. So the energy is generated right into the core, and then you have a radiative zone about 30%. And in the case of the sun, the 30%, outer 30% is convective and so on. So because of all these internal structure and their divisions, is a star can rotate differentially. And then what we now understand, that majority of the stars which are convective in nature rotates differentially. And that's one of the major ingredient of generation of magnetic field inside a star as well.
Thank you. Well, I'm sure it's much more complicated, but
Yes.
it's a very simple, nice description. Well, one of the questions on the YouTube chat box is, can we predict the solar storms the effects of it on the Earth?
Yeah, that is the area where everybody is interested and working on. It's hard. It is hard. So we are making progress. So to make a good prediction, what is important is first of all to understand why these solar storms happens in the first place. So now we understand that because of this magnetic changes and the timescales of these evolutions of the magnetic field, there is a possibility of the solar storm. Having said that, it is not always that just looking at the magnetic field or monitoring it every second, every minute for continuously, we are able to really predict very well, when it's going to evolve, say, tomorrow. Maybe, close to the time when things change more drastically, we are able to predict that there is going to be a flare. Having said that, there are many different techniques being applied, and in fact this is an area where a lot of AI ML applications, artificial intelligence is being applied, because we do have lots of data for last say 20-30 years now about flares, and when flares happen, what are the effects and so on. So you train your machine with all this data, and with that you can start predicting. Having said that, you see, if this ejecta would have come into the interplanetary space through a so-called vacuum or an empty space, it would have been much easier. But as I pointed out, that the outer environment or the global field of the sun is also changing. So we need understanding of the global field. We need to understand and all the ejecta are not having the same property. Some ejecta comes with 100 kilometer speed, some ejecta comes with 1000 kilometer speed. So all these modelings are happening, and we do have 60 to 70% of success about, there are two elements actually. One is the predicting when the flare will happen, and then predicting when this ejecta will arrive at Earth. So that's called the arrival term information, because that is also very crucial for our ionospheric research and communication research. And as Professor Sengupta mentioned, it is so much important to understand if there is a ejecta which comes with several thousands of kilometers, it will have much stronger impact on our satellites and the communication systems and all that. And it can really completely make you into the blackout situation for several hours. So, and I mean, you all understand how important it is today in the modern world. All the satellite communications, even if our mobile is off for a few minutes, we crib. So this is going to be devastating. So it is true, we are able to now make reasonable progress. And that's the reason I was just mentioning. I just received an email from another space agency, because ISRO is now talking about a lot of privatization. And interestingly, one of the space new company, they're asking, you have a PhD student which we can hire. So I think it's interesting days ahead, and the knowledge what we have is now getting fed into this kind of big modeling efforts in coming years. We are able to make some progress now. Yes.
Great. Thank you. Well, we have a few more very simple questions, naive questions. One of the questions on the chat box here is, due to the ejecta, you talked about a lot of ejecta, small scale, large scale, and so on. Due to the ejecta, is the overall magnetic field of the sun decreasing?
Yeah, it's a good question. Thankfully, it is not, because the magnetic field is getting generated inside the sun. And now we understand, now we sort of theorize it with the help of a dynamo theory. So essentially, there is a cyclic process. So the two major ingredient is the convection and the differential rotation. So these flux tubes come on the surface. Some of it is is thrown out, as you can imagine. Some actually goes back through this 11-year solar cycle. I did not talk about it at all. These sunspots, the strong ones migrate towards the equator, and the weaker ones goes to the pole. And from the pole, they are dragged back into the base of the convection zone, that is the interior of the sun, and the new field is generated. So this is a completely cyclic process, and that maintains the magnetic field in the sun. But of course, if the sun as a star evolves in millions of years, and the convective nature inside is very different, the sun will become a red giant, then the magnetic activity will completely change. So until that happens, in the main sequence phase, like, the middle age of its lifetime, the magnetic field is expected to have, be regenerated all the time. Having said that, we still do not understand why there were some period in the past, like that 50 years, which I said, it's called Maunder minimum, why there were no sunspots. Actually, there were sunspots. Probably they were not observed because they were tiny and the observing facilities were, not enough to detect them. But why they were tiny? There are now some theoretical understanding, but it is still not fully understood as well. But to answer you again quickly, we do have the magnetic activity preservation, so to say.
Great. Another couple of questions. You referred to a term called Lagrangian point. Your Aditya is situated in a point, vantage point from where you can observe the sun all the time, etc. So just for the purpose of the layman's understanding, what is a Lagrangian point?
Yeah, it's a good point. So essentially, for any two-body system in a three-dimensional space, there are certain point in space where if I put a particle, the force between that particle.
Would you like to go to that slide?
I was just going to dig that out. Yes, it is must be there earlier. Yes. Yeah, I seem to have lost where I kept it. It should be here. Yes. So here I've only shown one Lagrangian one point, but basically, if I sit here, the satellite, the force between the satellite and Earth balances the force between the satellite and the sun. Although this distance is only 1% because sun is much heavier, so that becomes a much more stable point, that once we reach there, you won't need that much of fuel to really. So of course it will be orbiting in a very big halo orbit, but it will only need very tiny little fuel to stay on that, because it's a gravitationally very stable location where the force between the sun and the satellite is balancing the force between the Earth and the satellite. Here, incidentally, in a two-body system, there are 5 Lagrangian points. L2 is here behind Earth, but that's not good for solar observation, but that's good for astronomy. And the James Webb telescope is actually at L2 location. And one can have also L4 and L5 location, which are further away. We are still actually have started talking about going to L4 because we can see the sun from one side. I do not have all that Lagrangian slide here, but essentially, L4 and L4 is here and L5 is here. So we are talking about going to other Lagrangian point also in future.
Great. See, one of the things that straight away comes to mind is particularly if the Lagrangian point, as you on your graph, it shows about 1.5 million kilometers. It's quite far away from the Earth and naturally outside the magnetosphere. So you have a solid payload there with a lot of complicated electronics that's driving all the experiments. Don't they get destroyed by the intense solar wind from the sun? Yeah. The Earth's magnetosphere is not there to protect them.
You are absolutely right. So that's, of course, a big concern. But still, we are, as I indicated, within the sun-Earth distance, we are only 1% of the distance. So it is still not that close to sun. But you are absolutely right. It doesn't get protected by magnetic shielding of Earth's magnetosphere. So it will have, impacts of all these particles. And so there are two things. One is, of course, we have the particle detectors to characterize these particles. So we want to study that. And the other thing is, unless we go out of magnetosphere, we are not able to really properly see this magnetic ejecta, appropriately. Now, to protect our systems and electronics, this is already very well tested in the laboratory. All the electronic components are hardened. So we have space qualifications for all these components. They are tested in the laboratories with extreme hardened radiations so that, they can sustain those environment. So this is a requirement from our point of view. And based on that, And that's why the components are 10 to 20 times more expensive than any component you name it, which is flying, is 10 to 20 times more expensive than its normal product.
Okay, great. Thanks. We just have one or two questions on the chat box, but before I take those, may I request our colleagues and friends on the panel in the WebEx meeting? Mila has raised her. Mila, please go ahead. Switch on your mic, your camera, and go ahead. Ask your question, please.
My apologies. I'm Krishna. I'm using Mila's computer and asking this question. This is a question regarding something that you mentioned in passing about the stratospheric UV connection. Since I'm from an atmospheric science community, I wanted to know what is the design life of this mission? So will it last through a full sunspot 11-year cycle? And secondary question is there a team that is involved in looking at the stratospheric chemistry and dynamics effects that this could have? Which group in India is involved in it? Thank you.
Yeah, it's a very, very important question. And in fact, so let me first answer your first question. So nominal life of the Aditya mission is 5 years. But when you say nominal, we expect Aditya to be there for one solar cycle. So that's the expectation, because SOHO is one of the Lagrangian 1 mission from ESA. It was launched in 1995. It is still there. All the instruments do not work with the same efficiency, but there are many instruments which are continuously taking still observations. They don't take observations continuously. They have periodic scheduled observations and all that, but it is still there. So that's the thing, that the satellite to stay there for a long period because of this advantage of the Lagrangian 1 location is very favorable. Having said that, the instruments has to last also, as Professor Sengupta mentioned. It's getting completely, continuously bombarded by these solar radiations. The storms and the solar wind. But still, the expectation is we will have it for one solar cycle. That's the first answer. The second is, this particular instrument is been built by IUCAA. And there are certain members I understand are collaborating with the IUCAA team, but not a very big team. This is, I would say, a little. I am still not fully aware that the full team is engaged with the atmospheric science. Having said that, we do have a collaboration with the Max Planck's Institute in Göttingen, and they were particularly interested in these near UV wavelength. They had a rocket flight. And they had also a balloon flight with similar observations. But as you know, those are very short period of time. And they published quite a few stuff from there. They were very keen to, and they're one of the collaborators as well. So the Max Planck group from Göttingen is heavily involved in this, this particular payload.
Thank you.
Thank you. Any other colleagues on the WebEx? Well, if not, I'll quickly take the last question on the chat box. It says, hello team, how passionate people working in other domains can contribute to this project? I suppose he refers to the Aditya L1 project. So
we are really looking forward for more and more people to be involved in this mission. And in fact, as I indicated, my personal emphasis is on that, to build the user community more. And as I indicated also in the beginning, although this is a solar mission, but we know now that everything has to be worked as a coupled system. All the Earth's atmospheric layers, communication system, solar radiation, solar interplanetary medium, it actually has to be worked in a heliospheric physics, not in solar physics anymore. So unless we have a really enthusiastic engagement from the entire heliophysics community, which includes Earth and other planetary atmosphere and solar physics community and so on, it will not get the equal success. And to do that, of course, the professionals who are already engaged is enthusiastic, has to participate. I'm trying my best to build the next generation also. So that's why I'm going to different universities, conducting these workshops, so that there are students in the engineering faculties. There are space weather is actually a multidimensional things now, and the kind of data what we are going to generate, the possibilities of all these, as I was taking automation applications in AML, and very different kind of image processing techniques do need involvement from multiple domains. So I am the entire Aditya core group is very much looking forward to larger participation. It is our responsibility now to reach out to let people know what this mission is capable of. Because what happens, we get engaged with building the instruments and then delivering it and all that. But now it's time. The instruments are in the final stages of integration. So I think we will really engage ourselves, and we'll be happy if people connect with us, and we will be mutually benefited on this process. So it's very, very important, and I'm quite enthusiastic about it.
Well, thank you again. That was a wonderful lecture, Professor Banerjee. I'm sure all our viewers have enjoyed it greatly, and we are really grateful to you for that wonderful and very visual, very pictorial description of the fascinating processes on the sun. Now, I have the pleasant duty of handing over to our colleague, Shri N.K. Vadva, who is the General Secretary of the NPL Former Scientists Forum, to propose a formal vote of thanks. Mr. Vadva, please.
Yeah, before Mr. Vadva takes over, I must again profoundly, thank you for, giving us this opportunity. And as I said, it's a very, very, prestigious forum. I wish I could see you all in person, but something is better than nothing. So at least it initiates this forum and exchange, and I'm really, really honored to be invited to give this talk.
Our pleasure. Our pleasure.
Our pleasure. Thank you. Dear dignitaries, Professor Dr. Venugopal Achantaji, Dr. Dipankar Banerjee ji, Dr. S. Anantakrishna ji, Dr. Amitabh Sengupta ji, Mr. R.B. Saxena ji, Dr. J.C. Sharma ji, family members of late Dr. A P Mitra ji, and NPL Former Scientists Forum colleagues, NPL fraternity, distinguished participants from InRaSS and abroad, my CSIR-NPL's friends, students, and also our audience watching us through this YouTube broadcast. We are extremely grateful to Dr. Dipankar Banerjee, Director ARIES, for accepting our request to deliver this 8th A P Mitra Memorial Lecture at very short notice. Sir, we are all enlightened by your very informative eye-opener lecture on the Aditya L1 India Space Laboratory to study the variability of our nearest star, that is the Sun. We convey our gratitude to Professor Dr. Venugopal Achanta, Director, CSIR-NPL, for presiding over this function and gracing this event with his encouraging welcome address. My deep regards and thanks to Dr. J.C. Sharma, who is president of our NPL Former Scientists Forum, who has always been a source of great encouragement and inspiration to the organizational committee and his FSF core team also. Our special thanks to Dr. Anantakrishna ji, President InRaSS, an eminent radio astronomer who has always been very supportive and a mentor to the radio science community and radio science society. Our special thanks to InRaSS for jointly organizing this prestigious lecture series with CSIR-NPL. We are grateful to the entire team of InRaSS and CSIR-NPL for this successfully organizing this event. I would take this opportunity to place on record my heartiest thanks to Dr. Amitabh Sengupta ji, Chairman, Dr. A P Mitra Memorial Lecture Committee, for the perfect logistic support and guidance he has extended to the organizing committee. My sincere thanks to Dr. Mr. Rajan Babu Saxena ji, the Vice President of NPL Former Scientists Forum, and also he is convener of this event for his successful coordination ability with organizing persons, institutes, and related management for organizing this event. I am also thankful to Dr. Hari Kishan, Treasurer, NPL Former Scientist Forum, who has very meticulously helped in the successful webinar organization. And I am also thankful to my Joint Secretary, Mr. V.D. Arora, for assisting me for this event. Now, on a special mention, we have with us today the late Dr. A P Mitra's family members who have graced this occasion with their presence. Since the initiation of Dr. A P Mitra Memorial Lecture Series, the family is associated with NPL Former Scientist Forum and has significantly contributed to this cause also. The forum is highly grateful to them. At the end, I thank all the distinguished delegates, invitees, and YouTube audience who have patiently attended this lecture. This reflects their respect and regard for the late Dr. A P Mitra ji. We look forward to meeting you all again next year. To stay updated on these dates for other details, we invite you to refer our website, that is www.npl-FSF.in. This may be around the last quarter of next year, that is 2023. Thank you all. Namaskar.
Thank you very much, Wadbaji. And now, finally, thanking Professor Dipankar Banerjee one more time, and we'd like to close this meeting. But with just a little request, Professor Banerjee, in case we, get any more questions or requests to connect up with you, we will probably take the liberty of passing on all these to you.
My pleasure. My pleasure.
Thank you. Thank you again for agreeing to give this talk with us. Hope we meet sometime in person. Thank you. Okay, I am closing this meeting. Thank you. Bye-bye.